So this is problem number 4 from the 2004 AP Calculus AB free response set, and what we're asked to do with this curve, and this curve is defined implicitly, it's not solved for y. We want to find the derivative of y with respect to x and show that it's equal to this. So if we take the equation of the curve and we do the derivative of both sides with respect to x, so we're going to do the derivative of the left side of the equation with respect to x and also the derivative of the right side of the equation with respect to x. If all goes properly here, we should be able to show that our derivative is in fact equal to what they're claiming it to be equal to in the problem statement for part A here. So we're taking the derivative of both sides with respect to x. The derivative on the left, well, the derivative of the first term is just 2x. So that's pretty simple. Now the derivative of this term, what we need to assume when we use implicit differentiation is that y is a function of x. So what we have here is we have this outer function for something squared and this inner function y. So we're going to have to use an application of the chain rule to take the derivative of 4y squared with respect to x. And the derivative of 4 something squared, if we multiply by the exponent and subtract 1 from it, we'd get this. We want to leave the inner function in place, and then we want to finish the chain rule by multiplying by the derivative of the inner function, and the derivative of y with respect to x is dy dx. Now on the other side, the derivative of 7 is 0, so that piece drops out. This constant I'm going to copy down into my derivative, and then I need to do 3 times the derivative of xy. Now x times y is actually a product of two functions of x. So I'm going to have to use a product rule right here and then distribute my 3 into both pieces of my product rule. So my first function of x is x, my second function of x is y. The derivative of x is 1 times the original second plus the original first, which is x, and then times the derivative of the second, and the second is dy dx. So we would end up with this after we apply the product rule. Now we want dy dx, so now it's a matter of solving for dy dx. The issue now is we have a dy dx on this term, we have a dy dx on this term. We're going to have to find some way to get a single dy dx in our equation before we can isolate it. So the trick that we've basically been using is to move everything that contains a dy dx to one side. Typically we let that be the left side of the equation. So I'm going to leave this 8y dy dx on the left side of the equation. I'm going to subtract 3x dy dx, so I'm thinking about distributing this 3 into both terms inside that quantity there. I'm going to subtract 3x dy dx from the left. I'm going to have to move this 2x over here with the 3y. So I'm going to have 3y and then minus 2x. And if you factor out dy dx as a common factor between these two terms, you're looking at dy dx equals 3y, I'm skipping a step here. If I'm factoring out, I'm looking at dy dx times the quantity. Well, if I factor dy dx out of this term, I'm left with an 8y. If I factor dy dx out of this term, I'm left with a minus 3x. That's equal to 3y minus 2x. And what's dy dx? Well, divide both sides by this quantity and you have your answer for dy dx. We'd be able to say that dy dx equals what we have to the right of the equal sign, which is 3y minus 2x, and that's going to be over 8y minus 3x. And if we look back up to what we were supposed to show what the derivative was, I think we have produced this exact expression. So our derivative is definitely going to be equal to this. Now in part B, we're going to need our result from part A. So I've already copied our derivative onto this screen. But part B says show that there is a point P with x coordinate 3 where the line tangent to the curve is horizontal. Find the y coordinate of this point. So if the tangent line is horizontal, the slope of our tangent line is going to have to be equal to 0. The slope of a horizontal line is 0. If our tangent line is horizontal, the slope of our tangent line must be 0. And so basically what we want to try to do here is we want to try to figure out when our derivative, when dy dx, is going to be equal to 0. So our derivative from part A is right here. And if we set that derivative equal to 0, we end up with 0 equals, I'm not even going to put the denominator into my derivative here, because the only way that a fraction can be equal to 0 is if the numerator is 0. So I set 0 equal to the numerator of my derivative, because that's the only time a fraction can ever be equal to 0, if the numerator is 0 and the denominator is not. And I realize I have an issue because I don't have any way to solve this for either variable right now and get a numerical answer. But it said show there is a point P with x coordinate 3. So they've told us what the x coordinate of this point is. So what I'm going to do is I'm going to take that x value and I'm going to put it into my equation that we're writing out here in place of the x. So we're looking at 0 equals 3y minus 2 times 3. So this would obviously be a 6. If I'm trying to now solve this equation for y, that's something that's pretty simple to do. We actually end up with a very simple equation. I'm going to add 6. I'm going to divide by 3. And I get y equals 2. Now here's the snag. We know that our derivative is equal to 0 when x is 3 and y is 2. The only thing that we don't know is whether or not there's a point on the curve where x is 3 and y is 2. We'll be able to take the original equation of the curve and put in 3 for x and 2 for y, and if we get a true statement, we know that that point is in fact on the curve. So I just want to double check this before we finish this up and move on to the last piece of this. I'm going to put 3 in place of x in the original relation. I'm going to put 2 in place of y, since that's the answer that we got down here. So we're looking to answer this question. I guess I should write it out here. Is 3, 2 on the curve? That's what we're trying to figure out. So we put 3 in for x, we put 2 in for y. On the other side of the equation, we're doing the same thing. So we're going to put 3 in for x, and we're going to put 2 in for y. And if we simplify, this is a 9. If we follow the order of operations here, we're squaring first and getting 4. 4 times 4 is 16, so we're looking at 9 plus 16. So I guess we get 25 to the left of the equal sign. And then on the other side, let's see, we have 3 times 3, which is 9, times 2, which is 18. And if you do 7 plus 18, you do get 25. So since this equation is true, we have confirmed that the point 3, 2 is on the curve, and that at that ordered pair, our derivative is going to be equal to 0. I don't have enough time to finish part C in this video, so I will do that in a separate video.